Good afternoon, everyone. We're about to start our webinar on teaching derivatives and antiderivatives using Sketchpad. The main part of the presentation will involve looking at two activities, one for introducing derivatives and the other for introducing antiderivatives. We'll have time for questions between the two activities and at the end, and we'll let you know how to find the resources that you need to use these activities with your students. We'll finish with some quick glances at several other calculus activities. I'm Scott Steckety, and I'm the presenter for this webinar. I taught math and computer science in Philadelphia for many years, and I've been doing Sketchpad software development, curriculum development, and professional development since shortly after the release of Sketchpad version 1. Assisting today is Elizabeth DeCarly, who will be available to answer your typed questions during the presentation itself. To start you off on the right foot, Karen Greenhouse, who has organized this webinar, will give you some information about asking questions, answering polls, and so forth. Karen?
Okay, well, welcome everybody, and what I want to just do real quick is give you a brief overview of how a webinar works, because I'm sure some of you have never been on a webinar before. So basically this is an online presentation, and you will be muted throughout the presentation, and this is to avoid background noises, dogs barking, and that type of thing while Scott is presenting. So during the presentation, your microphones will remain off, and if you have a question that you want asked while the presentation is going on, there's a couple of ways that we're going to address those. One of them is in your control panel, and if you do not see your control panel, it is on the right-hand side of your screen. If you don't see it, to maximize it, find a red arrow button or a double black button up at the top right-hand side. Click that. It will maximize your screen, and you should see the attendee list. You should see a question panel, and also on the left-hand side of the control panel, some little icons, one that looks like her microphone, one that looks like a little hand raising. So during the presentation, if you have a question, go to the question panel and type your question in and send it, and Elizabeth and myself will be answering those as the presentation goes on. After each activity, Scott's going to pause for a moment, and we're going to go through some questions that we want everyone to hear. And if you have a question that you also want to ask, you can either type it or raise your hand, and that simply means click the hand icon and it puts a symbol next to your name, and we can call on you and unmute your microphone so that you can ask your question out loud. If you don't have a microphone, you wouldn't use the hand raising because then we could not hear you. So you would simply type your question in the question panel. So at the end of the presentation, we will also have final questions as well, so either hand raising or typing. So hopefully we'll get to everybody's questions as the webinar goes along. And Scott, I'm going to turn it over to you to start.
Okay, thanks, Karen. I want to start by raising the fundamental question of why we'd want to use Sketchpad to introduce the most important concepts in calculus. I think there are several important benefits to students. Students become engaged with the mathematics when they create it themselves. Students can actually make H approach 0. You can't do this with static media. Students experience the fundamental role played by rate of change. And to finish it off, students come away with images and experiences that support the abstract concepts we want them to learn. I'd like you to think about these particular benefits as we look at these two activities today. By the way, either activity can be used as a whole class presentation or as a student activity. As I show you these activities, please think about whether they'd be more effective for hands-on student use or as a whole class presentation. Also think about whether you'd want to use this first activity as your introduction to derivatives before a formal definition, or whether the activity would be better as a follow-up and reinforcement after the formal definition.
Scott, I'm sorry, Scott, this is Karen. Somebody said that your voice is low, so could you speak louder possibly?
I can try to speak louder, yes.
Excellent, thank you.
I hope this is better. Okay. I'll try to use my teacher voice here.
There you go.
All right. So in this first activity, we're going to find the slope of the sine function. So let's see, to find the slope of the sine function, I guess I better start by actually graphing the sine function. So from the graph menu, I'll plot a new function, the sine of x. And here we have the sine of x. So now I ask my students, well, what's the slope of this function? We want to find the slope of this function. Wait a minute, my students say. Linear functions have slopes, but who ever heard of the slope of a sine function? Well, I have to admit that it's not quite as simple as finding the slope of y equals 2x minus 3. But what could we figure out about the slope of a sine function? And we have a bit of a class discussion, and maybe somebody says, well, if you put a line on that function, maybe then we could find the slope. So I say, okay, let's take Sketchpad's line tool, and let's start at one spot on the sine function and finish at another spot on the sine function. How does that look? That's the slope between these 2 points. Does that look good? And my students say, no, 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 that's not what we meant. And they finally convinced me to put these 2 points a little closer together. And they claim that, well, that's at least telling us something. But as they pointed out, it's not telling us a whole lot, because if we move that line along the curve, we see that the slope is continually changing. Okay, so what are we going to do here? Well, we are already using the moving secant to approximate the rate of change, and we're going to move in the direction of letting h approach 0 to improve that approximation. That's an aside to you as teachers. My students are hopefully going to come to the same conclusion by the end of this little activity. All right, so what can we do now, back to the students, what can we do to actually tell something more about the slope of this? Do you know when it's going up, when it's going down? When is the slope positive? When is it negative? How can you tell these things? And we have a little bit of a discussion about that in class. And at some point, they've made some descriptions, and I say, well, now it's time to look at this a little more exactly. So let's take that secant line and actually measure its slope. And let's watch that slope closely. What's the biggest value you ever see it become? And if you're watching very carefully, you probably see that it gets up to 0.9 something and down to negative 0.9 something else. And we talk about the behavior. When is it changing from positive to negative? When is it at the maximum? When is it at the minimum? So we're having a nice discussion about the behavior of the slope here. And then I say, well, now let's try to investigate this a little more exactly. And when we try to study a changing number in mathematics, what do we often do with that number in order to understand it better? And the answer comes out eventually in the discussion that, well, we make a graph. We show the number on a graph. So we would like this slope value, we'd like to graph that as a function of what? Oh dear, we have to have another discussion what it's going to be a function of. We talk about that for a bit, and they decide, well, one or the other of the 2 points, their x-coordinate would be a good thing to use. So we'll measure the x-coordinate of point A. So there we have an independent variable that shows where we are across the screen, and a dependent variable, which is the slope of the sine function. So I can graph those values to get a plot of the slope of the sine function as we move along the function. And I'd really like to keep track of where that plotted point is so that I can see how the slope varies as we go across the screen. So we watch it for a bit, and we compare where its maximum is with what the sine function itself looks like and where its minimum is and so forth. But students notice that something is wrong here. We really want this to be a function. And it's certainly not a function because we have two different traces on the screen. It fails the vertical line test. Well, what can we do about that? And we talk about it a bit, and students say, well, how about the fact that we picked A rather than B, and right now B is to the left of A until it hits and bounces off the edge of the screen, and now B is to the right of A, and I bet we could fix that if we just moved B and A a little closer together. So the idea of putting B and A closer together comes from the students based on the perceived problems with the graph that we're looking at. And to see what's happening now, hold on one second, I better erase my old traces so that we can see how the new traces are doing. But that idea of moving the 2 points closer together, having come out of the discussion, we get to see, well, how does that work? Does that help us some? Absolutely. This is much better than before. So let's move them even closer together. All right, we'll pause again, move them closer together, and continue with our traces erased one more time. And now the question is going to be, does this totally solve the problem? Are we exactly where we want to be with this? And they notice that it's slightly off as it's retracing. So the question becomes, well, let's just move B and A right together so that we get the actual tangent line instead of the secant. Let's try to do that. All right, so we stop our motion for a bit. Whoops. I meant to stop them both at once, but I failed to do so. Let me get A right next to B again. There we go. That's better. But we actually want them right on top of each other. In preparation for this, I'm going to erase the traces. We'll make a new set of traces in a moment. I want them right on top of each other, so I'm going to make a Sketchpad movement button that moves A and B to the same place. Here's my movement button. It will go at medium speed, moving B towards A. Here's the button. Let's go. Uh-oh. Oh dear. What just happened? Let me undo that. When I pressed the movement button, the line went away, and the slope went away as well. I guess that makes sense. If the line went away, the slope's going to go away. What happened? So we have a class discussion, and they eventually tell me that, well, that was just actually a silly idea we had, because if the 2 points are 1 point, we can't make a line anymore. So we talk a little bit now about the fact that we need to get those 2 points closer and closer and closer together to actually turn this slope value into a function, but we can't actually make that distance between the two 0. So now we've got the whole idea behind taking the slope, making h approach 0. We cannot let h actually be 0. We have to make it approach 0. So the importance of a limit and the importance of approaching that limit comes right out of the discussion that we've had. And we haven't done any deep algebra. We have looked at it and created an image that the kids can remember. Okay, so that's the first activity I wanted to show you. And we're going to pause for a moment now. We'll have a chance to ask questions, but first I want to put out, I promised there would be a quiz, and I want to put out a couple of quick polls for you. The first question on the poll is whether this activity is more useful as a preparation for the definition or as a follow-up. So if you would please answer that poll, and I'll share the results of the poll in just a moment. Okay. We have 90% of you voting already. So I'm going to close the poll and sharing the results. 86% said use it first. Seems to me it can certainly be valuable in either position, but I'm inclined, well, certainly I presented it that way. I like that. I like either approach, to tell you the truth. Okay, second poll. If you had ready access to computers, would you use this as a hands-on activity, or would you use it as a whole class presentation? Okay, let's take a quick look at these results. Very similar to the others. 86% whole class. I sort of prejudiced things because that was the way I presented it here in the webinar. So let's take a moment for questions, and I don't.
And Scott, there's nobody has a question right now that I can see. So if anyone does have one, you can either raise your hand or type it. If not, we'll move on. Just give everyone a couple seconds if they had a question.
And
okay, it doesn't look like it, so let's move on.
No questions at the moment.
Okay, don't forget to close your poll.
Oh, yes, thank you. There we go. Okay. So the second activity we want to take a look at today is introducing the antiderivative. So in this activity, we're turning our previous question on its head in this sense. What I have here is the slope function for some unknown mystery function. And by now we've already defined the derivative, so I can use that terminology and I'll say, this is the derivative of some function. I want to know what that function is. How can you figure out what the function looks like from its derivative? So let's see, how would we approach this? What we know is that the derivative tells us the slope at any point for any value of x. So for instance, for an x value of -4, I'll put a point right here at approximately an x value of -4. We can tell that the slope of the function we're looking for would be somewhere between, looks like somewhere between 1 and 2. And in fact, because we know this function, we can actually calculate it. We can actually say, well, let's calculate the value of the slope function at this value of x. So in fact, the slope is about 1.42. So what does that tell us about the function that we're looking for? It tells us that at this spot, the function we're looking for is increasing with a slope of about 1.42. So let's see if I can draw a tiny little bit of that mystery function, the function that we're looking for, the function that has a slope of 1.42 right here. Well, I could make a slope triangle. A slope triangle would entail going 1 to the right and 1.42 up, and that slope triangle would have the right slope for what we're looking for. That would be cool. But that's going to be an awfully big hunk of the function, and I really only want to show a little tiny bit of the function right here. So I'm going to do something slightly different along that same idea. I'm going to create a parameter that I'll call h, and I'll give it a value of 0.5. And instead of using 1 for my run and 1.42 for my rise, I'll use 1/2 for my run and figure out an appropriate rise for that. Okay, so to use 1/2 for my run, that means I need to add 1/2 to the value of x. So let me take the calculator again, the value of x plus the value of h. So that gives us negative 3.46. That's going to be 1/2 to the right. And now I need to go from point A up by the appropriate amount based on what we know the slope is. All right, so let's see. Better begin by actually measuring the y value of point A so I know where to start from. And now I'm going to calculate based on the y value plus the rise. But wait a minute. I don't want that whole rise because that full rise corresponds to a run of 1, and I've only got a run of 1/2, so I better use 1/2 of my rise. So I'll put h times the rise that I calculated. So this should be the new y value for the end of that slope triangle. My slope triangle should go, here's the run, here's the rise. Let's graph that point and connect them. And there's the slope triangle, or the slope that we're looking for. Okay, so hopefully that makes sense to folks. Let's see if that really corresponds with what we know about the slope, though. Let's see. If I moved A over near this intersection where the slope is 0, what should the slope on this little segment look like? A slope of 0, it should be horizontal. Let's see if that actually happens. I'll move A to right underneath that intersection. Yes, it is horizontal. Here the slope is positive, so for this entire stretch, I should have an increasing function. The slope should be pointing upward. Now we're back to a 0, so horizontal again. Here the slope is negative, so the function we're looking for should be a decreasing function, should have a negative slope. So it certainly looks like this little segment we've created is doing the right thing. All right. So we know right here, for instance, that the function is supposed to be decreasing. I'm going to try to take my segment and use this segment to figure out what the antiderivative really looks like. So let me take the segment and trace it. And I need a decreasing function now, so I'm going to drag with my mouse in the direction that's shown to me by my probe, by this segment. Now the function is increasing, so I have to start moving up. And it's increasing more quickly. So I start moving up a little more steeply. I'm still trying to follow this segment that I've created here, because the segment is telling me where to go at every moment. Now it's tipping over and getting more horizontal, so I'm trying to drag again. Horizontal, always trying to follow the segment that I created. Okay. Decreasing function here. So I'm trying to follow my probe again. Tipping over. And now it's increasing quickly. Oh my goodness. Okay. So this function that I've traced out should be approximately the shape of the function that we're looking for. And what I've done, if I trace this out, created this and traced this out as a student, is I have tried with my mouse to follow the slope in order to create the antiderivative, in order to create the function whose derivative I've been looking at. Now, there's an interesting thing about this process, though. Let me undo back to the beginning here. The interesting thing is, I could have started somewhere else. I could have started, for instance, right here and done the same kind of tracing. I could have started here, decreasing function right there. We're at, the slope is 0 now going up, okay. Approaching a 0 again, horizontal, decreasing function again. So tracing it, whoop, another turn, and up we go. So I could have started anywhere. In fact, I could have started here or here. I could have started here, although I'd have quickly gone off screen in my tracing process, so that might have been a bad place to start if I really want to do this with the mouse. But I could have started anywhere to trace it out this way. So immediately I conclude that there must be more than one antiderivative. In fact, there can be a huge number of antiderivatives. So what do they have in common? What's different about them? What's the same? So we investigate, we have some questions about that in the activity. And hopefully students notice that, well, this shape is really pretty similar to that shape. And they do a few more, and they find that the shapes are similar again and again. All the shapes are similar. So we have many antiderivatives, but they do seem to differ. At least we have a conjecture that they differ according to their height on the screen, but not in shape, that they stay the same shape. Now, we'd like to confirm that conjecture, but that's a little hard to confirm a conjecture like that when we've been tracing these out by hand. The tracing by hand is very important because it gives the kids a sort of the kinesthetic sense of trying to do what the slope function tells them to do. In fact, it's a manual version of an Euler approximation, dragging a little bit according to what the slope is supposed to be, reevaluating the slope, dragging a little more, reevaluating, dragging. Exactly an Euler approximation here. But we can get Sketchpad to do this automatically as well. I wouldn't start this too early because the hand work is very important. But now that we've done that, I'm going to turn off tracing. No, I'm sorry, I'm not turning off tracing yet. I'm going to erase my traces and pick a bit more reasonable starting place, let's say right there. And I'm going to tell Sketchpad to do the tracing, to do the movement itself. I'm going to tell Sketchpad to move point A toward point B. So to do that, I select both A and B from the Edit menu. I create a movement action button. And here's my button. So let's tell Sketchpad, move A towards B, and as B changes, keep trying to move toward it. So here we go. That's a much smoother trace than I was able to make. Sketchpad's very steady about this stuff, I guess. Okay, so there's one trace. Back to the starting place, let's take a different, for you, I can say constant of integration. I don't say that to the students this early, but so we do another one. Is it really the same shape? Looking pretty good. Okay, so there's a second one. Undo, back to the beginning spot. Let's start from way up here. So there's another one. And we can do as many of these as we like. And they certainly do look like they have very similar shapes. There's only one problem. We might have a little discussion about this in class because students might notice, for instance, that these top two functions, these top two curves, are pretty far apart here and very close together here. So we'll need to have perhaps a bit of a class discussion about that. And one thing we could do is we could say, well, let's put a segment right here to measure the vertical displacement from one curve to the other. So that's about the distance between those two curves. And if I look at the vertical displacement over here, I see that actually it's about the same. It's just because the slope is different, they look closer together. But the vertical displacement between these two curves that we've traced seems to be about the same everywhere, even over here where they're very nearly touching. So what have we concluded from this? We've concluded that with this Euler approximation, we can trace out what the antiderivative looks like. So we have a sense from knowing the derivative of how we can find the antiderivative. And we've done it by hand, and we've done it automatically. We can even do one more slightly neater thing with it, and that's this. Let me get rid of this measuring device, put my point back, whoops, okay. All I really meant to do was to move point A back over to here. I'm going to turn off tracing now. So I've selected the segment, turned off tracing for it. I've erased all my traces. And what I'd like to do now is tell Sketchpad to actually do that Euler method reevaluation by finding this segment, as I did, from point A to B, and then find the next segment from B to the next spot, and from that point to the next one, and from that to the next one. That's called an iteration in Sketchpad. To create it, all I need to do is this. Select point A. From the Transform menu, choose Iterate, and tell Sketchpad that I want to do that same operation, the same operation that I did at A, I want to do at B now. And Sketchpad goes ahead and does that, and it does the same operation there and the same operation there. So I'm happy with this result. I have a table of values. I'll mention that in a moment. And I have several of these little segments that I created. The default is 3, but I can select the properties of this iteration and say instead of 3, I want 100. Okay, there we go, 100 of them. Excellent, excellent. Before I get rid of the table, we don't really need the numeric information right now, but I just want to observe that this table actually does say what we did in the Euler approximation. It says what our first value of x was, what the slope was. It gives the exact details of the rise and the run that we applied to it to get to the next value of x. And that next value of x, the x of a plus h, that's the starting place. Negative 5.85 is the starting place for the next row in the table, and the starting place for the next row on the table, and so forth. So we really have a table as if we did an Euler approximation by hand, doing it with a calculator. So we don't need that table for right now. And the other thing we don't need is I don't really care about the points. The points represent point A as it goes along. So I'm going to select that and delete it. All we really care about is these little segments that we have. And you'll notice that the segments are pretty choppy here. Especially, they're not too bad where there's not much curvature taking place. But where the function curves around, it's really pretty choppy and suggests that our approximation is not very good. So let's make the value of h smaller and take smaller and smaller segments. And by selecting h and pressing the minus sign on my keyboard, I can change the value of h to make it smaller and smaller and smaller. So let's watch what happens to the jaggedness, particularly around this sharper curve here, as I keep pressing the minus sign. And we see that it gets smoother and smoother and smoother as we use smaller and smaller values of h. Except that I can't see that curve anymore. And why was that? We only did 100 iterations. And our value of h is so small that we've used up all 100 iterations already. So let's do 1,000 iterations instead. Or what the heck, let's do 2,000 iterations. Okay, so now as h is approaching 0, let's keep a close eye on how much the overall shape of this function changes as we continue to get closer and closer to 0. So down to 0.08, 706, 5, 4, 3, 2, 1. The difference between 200ths and 100th is really very small. We could certainly go down into the thousands if we wanted, but you know what? We're not going to see too much difference anymore, at least within the limits of the screen. So we've again seen how the limit as h approaches 0 allows us to find the antiderivative in a very effective, very accurate way. And between the two parts of this, the manual tracing of the antiderivative and having Sketchpad do it automatically, we've seen an awful lot about how the derivative relates to the antiderivative. We've seen how the shape of the graph doesn't change as we drag up and down. And we've seen how important it is to take small steps and reevaluate and let h approach 0 in order to get this calculation to be accurate. So that's the antiderivative activity. And we'd like to ask you a couple of questions about this activity now. First question, this activity, is it more useful as preparation for the definition or as a follow-up as you're introducing the antiderivative? How would you use it? Okay, so we're coming out the opposite from the first one, using it later to reinforce the concepts rather than at the beginning to prepare for the definition. And second question, if you had it available either as hands-on activity or as a whole class activity, how would you use this activity with your kids? So this one's coming out pretty close to half and half, with clearly advantages both ways. The kind of whole class discussion you can get going with a whole class activity is very nice. The actual hands-on building of the little hypotenuse of the slope triangle and actually trying to trace it out by hand is a wonderful thing for kids to do and really helps them remember what's going on. So both are really good ways to use it, I think. Okay. Do we have questions? Actually, let me go to the next page here, and I have to hide the results. There we go. Okay.
Scott, there are a couple questions that we kind of saved, and then we'll give everyone time for more questions. But one of the questions was there any particular reason that you chose sine? The sine function.
Oh, for the first activity, for the
right.
For the slope function.
Right.
For the slope function. Yes. The sine is actually it's a lot easier. I mean, the alternative, an easy alternative, for instance, would be a quadratic function, y equals x squared minus 3x plus 2 or some such thing. And an awful lot of that graph goes off the top of the screen. So there's a lot of the action that is lost. You can still, when the point is off the top of the screen, you can still see that secant line, but you don't see where it's attached to the curve anymore. So having a curve that stays within the limits of the screen all the way across is a very nice thing to do. One can certainly do that with an appropriately chosen polynomial, but you have to choose your polynomial pretty carefully.
Okay.
So that's basically the reason.
And here's another question. Why not call, and this is for this particular activity, why not call this function f prime of x rather than f of x to reinforce the idea that it's an derivative?
That's not a bad idea. There are different approaches taken in different books. I've seen some books that will say, well, here's f prime, you have to find f. And I've seen other books that say lowercase f is the slope function, or is the original function, and the antiderivative is uppercase f. Okay. So there is a difference in notation that's used when you look at it in different places. There is no reason whatever why you can't tell students, if they're doing this as a hands-on activity, to call it f prime of x. They can change the name of that function very easily. So I could just say, well, let me go into the properties here, change its label, and make it f prime. There we go. So now it's f prime of x. Okay, other questions?
I have one more from the question panel, and then we'll open it up. It said, wouldn't this also be a good sketch to demonstrate that the derivative is degree 3, while the antiderivative looks like it would be degree 4, or at least some even degree?
That's absolutely an extremely valuable part of the discussion we should be having, and this makes it even a little clearer. If I go a little bit farther to the left, we can pretty well see that what we're seeing here is indeed a degree 4 function. So that's a wonderful discussion to have come out of this. Great question. Okay. Any other questions? Any hands raised?
Just so everyone knows, if you have a question now and you would like to actually ask it out loud, in your control panel there's a little sidebar, and you should see a little icon that looks like a hand. And if you click that, it will let us know that you have a question you'd like to ask out loud, and we will call you by name and actually turn your microphone on, and you can ask your question once you hear your name. So I'll give everyone a chance if anyone has a question and like to ask it out loud.
Okay.
Not seeing any.
Well, please feel free to raise your hand and ask a question at any point while I give you the quick glance at three more things that I think are kind of fun and that you'll I think you may find valuable.
Karen, there are a couple people who have questions that don't have mics that are already.
Oh, okay. So
I sent them to you on chat, and they're
okay.
They're towards the bottom.
Oh, here's a question, Scott. Can Sketchpad do a regression to find the specific antiderivative?
To find a specific antiderivative, certainly. Let's see. What would we do to find a specific antiderivative? If we wanted to say, for instance, that the constant of integration was 3, I could put point A at 3. I could actually assign it this coordinate and place it at this position 3 on the y-axis, and then we would have that specific antiderivative, which we would find as if we did it symbolically, we'd have whatever it is, x to the 4th, x cubed, x squared plus d times x plus 3. So yes, we can do that. The iteration only goes in one direction from there, so if I wanted to show both directions, I could actually do a second iteration in which my value of h was negative and I was moving to the left, and then I would see both branches and both pieces could be attached to the constant of integration of value 3 or 2 or whatever we assigned it. Other questions?
Yes, we got a couple. Is there an easy way to find the area between the derivative and the x-axis and compare that to the y value of the antiderivative?
Yes, by constructing a Riemann sum. And so that takes us to one of the activities that I want to show you here, one of the sample sketches that you will get with this zip file. And what we've actually constructed here is a Riemann sum with upper and lower limits for the sum that are adjustable. The function itself can be changed. In this case, you can leave it as a third-degree function and vary the coefficients. So everything is variable here. We see 3 Riemann sums together. You'll get a sample sketch that has each on a separate page as well as this combination of all 3. So we have the lower sum, which is the shorter rectangle in each of these places, the upper sum, and the midpoint sum. And we get to see, if we animate the increments, more and more increments, we get to see, let me do it with the plus sign on my keyboard for speed here, but we get to see how the upper and lower sum actually squeeze the midpoint sum in between them. And this particular sketch actually adds up the areas of all these rectangles, and here's the upper sum, here's the midpoint sum, there's the lower sum, and because we can do this analytically, we've also calculated the actual definite integral, which at this point, to this level of accuracy, is indistinguishable from the midpoint sum. So yes, we can do that, and in fact, if we were to, so let's see, if we, what would we need to do here? I haven't actually taken this to say, well, if we start from here, we could actually see how the upper sum, I'm getting into dangerous territory here because I'm totally ad-libbing because I haven't used this activity in this particular way yet. But if we plotted the x value of point B and the upper sum and trace that point, and then I get to okay, so we're going off the screen there. Well, this, I don't know if this construction breaks as I go into the negatives. Okay. So I think you can see that we're getting a 4th degree function here, which should be exactly the same 4th degree function that we would have gotten for this particular function if we'd done the antiderivative activity. So we could do them both on the same sketch. I have never done that, but I need to do that because that's a wonderful idea. Thank you for the suggestion.
All right, Scott, there's another question. And I just lost it. It says, when I iterate a distance along a curve to find arc length, the table gets a row of ellipses, I guess parentheses. Is there a way to get all the details so I can see and add the lengths of each segment?
The answer is yes, there is. And it's very similar to the technique that we've used here to add up the sum of all these rectangles. And unfortunately, the answer as to how to do it is too long for the time that we have remaining. So I would like to get an email address of the person asking the question
actually the
maybe
question...
more people want to know... Yes, go ahead.
Can I just say, all of those of you who are asking questions, if we don't get to your questions, I print a report and it has all your questions included, and Scott does get a copy of that, which has all your emails, so he can answer individually any questions that we don't necessarily get to today, or for, like, example, this one, it takes too long to answer. So he will see your questions and he will be able to respond to you after the webinar.
Good, thank you.
Let me just make sure I'm not missing any questions here. All right, here's a question. My question about Sketchpad's ability to do a regression to find the antiderivative wasn't worded clearly. I'm not asking about a specific constant of integration. I am asking whether Sketchpad can figure out the equation of the antiderivative in order to compare it to the result found symbolically. In other words, can Sketchpad find the indefinite integral?
No. Sketchpad doesn't have that analytic capability and is not likely to. This is actually one of the issues that comes up as a result of the fact that we can change these functions in any way we want. So here we have a polynomial. Okay, that's easy enough to analytically determine the antiderivative or the indefinite integral. But I can edit this at any time to be any other function. So I can turn this into the sine function. And that didn't look very good because this sketch happens to be showing its units in degrees rather than radians. And the value of a is very small, but there we have the sine function. So everything that we've done applies to the modified function. If Sketchpad also had the capability of finding the antiderivative analytically, we would have a serious problem when I start editing this function into something that cannot be integrated analytically. And there are many such functions. We don't want our Sketchpad constructions to disappear just because we've changed the function that we're using. So that's a roundabout way of justifying and explaining the fact that, in fact, we can't do that at this point. Any other questions?
Yeah, here's one more. How are a variable number of areas added?
I'm not sure I understand that question. How are a variable number of areas added? We have a variable number of areas here, so this may again be the question of how do we accumulate the areas of all these rectangles? And
okay.
That's the question that's that I'm not.
That's too long.
There's not time to answer. It's too long for this time. Yep. I have a couple other quick things I want to show you.
I do see one hand raised. Did you see Anthony up at the top?
Oh, yes. So let's unmute Anthony's mic. Anthony, are you there?
Yes. Did you
Go
hear
ahead.
me?
Yes, we can hear you.
Go ahead.
Yeah, very simple. I'm operating Calculus in Motion with Sketchpad version 4.0, and you are operating with 5.0. Is there any difference? Can I do all of this with 4.0?
Everything that I've showed you here, you can do in version 4. And there's one other piece that I want to show you. I'll point out to you the class pass in just a second, which gives you access immediately to the sketches and the worksheets for both version 4 and version 5 for the antiderivative activities. So yes, both activities can be done in either version of Sketchpad.
Great, thanks.
Okay, two more quick things, 15 seconds on each. Here's a slope field sketch you'll be getting. This particular Euler's method approximation is for this differential equation here, x over y squared minus 4. We can change the initial conditions and see what different initial conditions do to the to the solution to the differential equation. The other thing you'll be getting is this sketch, which allows us to create a wireframe for any particular function that we decide to use. This is the function sine of x plus 2 rotated about the x-axis. And this is a nice way for students to be able to get a picture of what these functions look like when they're revolved around an axis. Okay, back to the resources page. One of the resources you notice here is the ClassPass, which gives you access to the webinar sketches and worksheets. And let me find, oh dear, I had this ready for you. Can you see this? So this is where the ClassPass is going to take you. This is a Sketchpad lesson link student page that I've created for this webinar. And by scrolling down on this page, and I'll put up the URL again in just a moment, by scrolling down on this page, you see here's the activity for automatically probing the antiderivative. This is the Sketchpad 5 version. If you scroll down, you will also find the Sketchpad 4 version. So you can go to this URL right here to go to that student page from Sketchpad Lesson Link and pick up these sketches and worksheets right from there. Now that is designed for students, so you will also be getting the same information within the zip file if you download the zip file later on. You will be getting the webinar, a link to the webinar recording as well as the link to the zip file. And these are additional resources that may be of interest to you. Anthony talked about using Calculus in Motion, which is not a Key Curriculum Press product, but is of great interest to many calculus teachers. It's a calculus-based set of demonstration sketches and the Sketchpad constructions of the free response questions for the last probably 15 years of the Calculus BC exam. So those are the resources available to you.
Can I interrupt, please? I have a couple questions I just want to kind of address to everybody. People are asking about the emails you're going to receive about all the links. All the links that you see here will be in a follow-up email that you're going to get. I think I have it set to go out on Thursday. It will include the link to the recorded webinar, the link to the zip file, also the link to the Sketchpad lesson link, ClassPass, where you can actually see these sketches in one place. All of these links will be included in that email as well. And also, someone asked about future webinars. We do plan to be offering Sketchpad webinars once a month on a regular schedule. I believe, Elizabeth, it is the first Monday and Tuesday of every month. Am I correct?
No, it'll be the third.
Oh, it's the third Monday. I'm sorry. The third, and yes, we will have a calendar of those going up on our website. And there will be emails sent out to let you know about those as well. And there'll be different content based. There'll be geometry, algebra, elementary, middle school. So once a month we plan to offer these webinars as well. And they will all be recorded so you can always see them on demand, that type of thing. We are going to end the webinar now. It is 7 o'clock. And so all of you who did not get your questions answered, we will have a list and we will answer those in follow-up emails, and thank you for your time. Scott?
Thank you very much, everyone.
Oh, survey, follow-up survey.
Oh, that's right. When the webinar closes, there is a quick 6-question survey, very short answers, and if you have any questions that either did not get answered or that you just thought of now, go ahead. There's a spot on there for a free response where you can type in any questions that you did not get answered, and we will make sure that we respond to those as soon as we can. So thank you very much for joining us. We appreciate your time, and have a wonderful evening.
Let me just add that I'll be grateful for any comments or suggestions that anyone cares to make to me. Thank you very much.